So in this video, I'm going to explain how to determine the percent composition of a compound, and then I'm also going to review how we convert between units of mass, moles, formula units, etc., which introduces us to the concept of stoichiometry, which we will address in the next video. So here, to determine the percent composition, if I'm actually given the mass of a compound, so specifically here I'm told that I have 1.6 grams of zinc and 0.9 grams of copper, all I need to do to find the percent that is copper is take the mass of copper, which is 0.90 grams, and divide it by the total mass of the penny, which when I add the two masses together would be 2.50 grams. I'm now going to multiply that by 100%, and what I get for my answer is 36%. Okay? However, if instead of being given the mass, I'm simply given the chemical formula, what you need to do is you need to determine the molar mass of carbon, put that on top, and then take the total molar mass of your compound and see what percent of that entire molar mass carbon is a part of. So if I take carbon, and the molar mass of carbon is 12.01, and I multiply that by 6 because I've got 6 carbons, the molar mass I get for carbon is 72.06 grams per mole. Then I'm going to divide that by the total molar mass of glucose. So 12.01 times 6 plus 12 times 1.008 plus 6 times the molar mass of oxygen, which is 16. And so what I get here is 180.156. And then I'm going to multiply that by 100%. And so what I end up getting, I round to 3 sig figs. If you round to 4, that's fine. It's a little bit ambiguous for these problems, how to round. I get 40.0%. So that's how to find percent composition. If you're given the mass, awesome. If you're not and just given the chemical formula, use the molar mass of your atoms and your total molecule. The last thing that I need to talk about in this video is Avogadro's number. So talking about converting between mass, moles, volume, and particles. So remember, the mole is your central unit. So if I'm wanting to go from mass to moles, remember the conversion factor for that is your molar mass. And that's what we calculated just a second ago when we were doing the percent composition. If I'm going from moles to particles, remember for particles, if you have just a single atom, it would be atoms. If you have a molecular compound, it would be molecules. If you have an ionic compound, it would be formula units. The value you're going to be using there, that is Avogadro's number. So 6.02 times 10 to the 23rd. And then if I'm wanting to go from moles to volume, I can do that. There are 22.4 liters for every 1 mole, but I must be at STP, which is standard temperature and pressure. And so the temperature at standard temperature and pressure is 0 degrees Celsius, and the pressure is 1 atmosphere. So if I'm under those conditions, I can assume that 1 mole equals 22.4 liters. So the molar mass equals 1 mole. 6.02 times 10 to the 23rd, either atoms, molecules, or formula units equals 1 mole, and then 22.4 liters equals 1 mole. So let's work on some conversion. So I'm given in this problem 0.5 moles of C6H12O6, which is glucose, and I'm asked to go into grams. Well, I want to get rid of moles, so I'm going to put it on bottom, and I want to get into grams. So going from mass to number of moles, I need to use my molar mass. So in 1 mole, I need to calculate the molar mass of glucose, and we actually did that in the previous problem. The molar mass is 180.156. And so what I'll do for my answer is I'm just going to take 0.5 and I'm going to multiply it by 180.156, and I will get my answer, which is 90 grams because I want 1 sig fig. So we're now going to add a little bit on, and instead of just having one conversion, we're actually going to go, for example, from grams to formula units, which requires 2 steps. So I'm going to start off, I'm in grams of sodium sulfate, and in order to get into formula units, I need to get into moles first. So I'm going to put grams on bottom, and I'm going to put moles up top. Now I've got to put the molar mass of sodium sulfate on bottom, so it's 142.05. I'm now in moles of sodium sulfate,
and I have to get into formula units. So I'm going to put moles on bottom, and I'm going to put formula units up top. Remember, you've got 6.022 times 10 to the 23rd formula units for every 1 mole. Okay? And now I can actually figure out how many formula units that is, and it's 1.93 times 10 to the 23rd formula units. Alright, so now instead of just doing one simple conversion from grams to moles or moles to grams, you now can go from grams into moles and then get into something else. What happens if instead I'm asking for the mass of, for example, iron, when I give you the mass of iron oxide? Well, I can do, it's extremely similar to what we just did, except now I've got to figure out how much iron is in that iron oxide, and in order to do that, I have got to use a mole-to-mole ratio. So what I'm going to do is I'm going to start off in 25.0 grams of iron oxide. I'm going to get into moles of iron oxide. So I'm going to put grams on bottom and moles up top. 1 mole for every, now I got to put the molar mass of iron oxide, which is 159.7. Now I'm in moles of iron oxide. In order to figure out the mass of iron I need to get into moles of iron. So I'm going to put moles of iron oxide on bottom and moles of iron up top. If you look at the formula, for every 1 mole of iron oxide that you've got there, you've got 2 moles of iron. So it's a 2 there and a 1 there. Now I'm in moles of iron, and it's very easy for me to get into grams of iron. So I'm going to put moles on bottom and grams up top again. Got to put the molar mass of iron, which is 55.85 for every 1 mole of iron, and then I can get my answer, which is 17.5 grams.
So in this video, we're going to go over how to determine the empirical formula for a molecule. And so really quickly, just as a review, remember the empirical formula is the formula with the simplest whole number ratio. So once I calculate my empirical formula, I can actually calculate my molecular formula, which I'll show you how to do. But let's first look at this example. So it tells me I have a compound with carbon, hydrogen, and oxygen. I have 9.1% hydrogen. I've got 54.5% carbon, and then the rest is going to be oxygen. Well, if I assume that the total mass of my sample is 100 grams, if that were the case, then I would have 9.1 grams of hydrogen, I would have 54.5 grams of carbon, and then I would take 100 and subtract those two from it, and I would get 36.4 grams of oxygen. Okay? And so now what we need to do, because remember, to write the empirical formula, you need C, H, O, and you need subscripts here. That's what I'm trying to determine. And these represent the number of moles. So I've got to take this value and I've got to convert it into moles. So 1 mole of hydrogen, what I'm going to put on bottom is the molar mass of hydrogen, which is 1.008. I'm going to do the same thing for carbon. 1 mole of carbon, but keep in mind the molar mass of carbon is 12.01 grams of carbon. And then I'm going to do the same thing but for oxygen. So 1 mole of oxygen, and it's 16 grams of oxygen. So when I find the moles of hydrogen, I get 4.538 moles. For carbon, what I get is 9.0278 moles. And then for oxygen, I get 2.275 moles. And so what I need to do, because you can't just round these values, what I'm going to do is I'm going to divide all of these by my smallest number of moles, and hopefully that'll give me whole numbers, because you can't just round this to 5, this to 9, and this to 2. Okay? So I'm going to divide by 2.275, because that's my smallest number of moles for each of these. And then I'm going to write out my number of moles. So here this becomes 2, that becomes 4, and that becomes 1. And so this becomes C2H4O, because it's a 1. Alright? Really quickly, I'm going to skip B, I'm going to go to your tips. First of all, when you are writing out your number of moles, write out at least 4 digits, because if you overround, you won't end up getting a whole number when you divide by your smallest number of moles. The next thing, you can only round a whole number if it is within 1/10 of that number. So for example, here, let's say 4.5, I can't round that to 5 because that's not within one decimal place. But for example, here I got 1.99. That's within 1/10 of the number of 2, and so that works. In the example I gave you here, 1.03, that's fine to say that's 1. If that were 1.3, no, you couldn't round that to 1. Okay? And then the other thing is, well, if you're in the situation in which you're not within 1/10 of the number you need, for example, if you had 1.5, what you can do is multiply the entire thing by 2, for example, to get 3. Or if you have 1.2, for example, you can multiply all of the subscripts by 5 to make that equal to 6. Okay, so that's an option, but I didn't need that here because I ended up with a whole number. Now, here it says a compound with an empirical formula of C2H4O, which is what I got, has a molecular mass of 176 grams per mole. What is the molecular formula? So what you're going to do is you're going to take the molar mass, which is 176, and you're going to divide it by the molar mass of your empirical formula. So the molar mass of your empirical formula for C2H4O is 44.052, and that's going to give you a whole number. And in this case, I get 4. What this 4 represents, I'm going to take my empirical formula and I'm going to multiply it by 4. So instead of C2, I'm going to end up with C8H16O4, and that is my molecular formula. So you take the molecular mass, divide it by the empirical mass, get a whole number, and then multiply your empirical formula by that value to get your molecular formula. And that's it.
In order to determine empirical formula, what you just saw was a fairly simplified version of finding empirical formula. All the information is given to you. You get into moles, divide by your smallest number of moles, and then you can determine your empirical formula. Well, what if it's not so obvious? Okay, so let's look at a problem here. If you notice, it tells you that the compound only has carbon, hydrogen, and oxygen. Okay? You've got a sample that burns an oxygen, and it produces that amount of carbon dioxide and that amount of water. So it says calculate the individual masses in that sample. Well, it's going to be pretty easy to figure out carbon and hydrogen. Just like what I did previously in going from grams of a compound into grams of that element, I can go from grams of carbon dioxide into moles of carbon dioxide into moles of carbon, and then get into grams of carbon. Okay, and so that's exactly what you do here. So you start off with a mass 1.9061 grams of carbon dioxide, get into moles of carbon dioxide, get into moles of carbon, and then get into grams of carbon by multiplying by its molar mass, and that is the mass of carbon that you get. Okay, you can do the same thing for hydrogen. Now the only different thing here for hydrogen is that for every 1 mole of water, there are 2 moles of hydrogen. Okay, so I'm going to go from grams of water into moles of water. Then the ratio, the mole to mole ratio, is 2 to 1. You've got 2 moles of hydrogen for every 1 mole of water. And then you can get into grams of hydrogen, and there you go. You've now got grams of hydrogen. If you notice, oxygen is in carbon dioxide and water. So what I can do, instead of trying to get into grams of oxygen from both of those, what I can do is say, all right, I know that I start off with a sample that consists of carbon, hydrogen, and oxygen. I know that I have 0.5202 grams of carbon and 0.03771 grams of hydrogen. The rest of that must be oxygen. So I'm going to take the total mass of the compound, which is 0.7579. I'm going to subtract the mass of carbon from it and the mass of hydrogen from it. And there I've got my mass of oxygen. So now we just solve for A. We figured out the mass of carbon, hydrogen, and oxygen. Now this is just a typical problem where I've given you the mass of your 3 different elements. Now we need to convert into moles of each of those elements, divide by your smallest number of moles, and then figure out the empirical formula. So let's do that. For moles of carbon, that was the mass of carbon I solved for on the previous page. I'm going to divide by the molar mass. There are my moles of carbon. I'm going to do the same thing for hydrogen. Okay, there are my moles of hydrogen. And there are my moles of oxygen. Remember, what you have to do now is decide which of those is the smallest value, and that would be the moles of oxygen, the 0.01231. So I'm going to take all of those values for moles and divide it by the 0.01231. And that's exactly what I did there. Okay? And so what I get is 3.5 moles of carbon, 3 moles of hydrogen, 1 mole of oxygen. While I can round the 3.039 to 3, that's fine, I cannot round 3.5 to 4 because I have to be within 1/10 of my whole value. So instead what I have to do is take all of those numbers of moles and I now have to multiply by 2. So the empirical formula that I get is C7H6O2. So this problem is extremely similar to the empirical formula problem that we did previously. It's just added on the component of having to figure out the mass of each of your elements before you've started.